Hey everybody, welcome back to the PyTorch 2.0 Ask the Engineer series. If you've been following along, welcome back. If you're new, this is the series where you get to ask your burning questions about PyTorch 2.0, ask our engineers and get them answered in real time. And if you've been following this series, you know the main topic or main theme is about performance, and today is no different. We'll talk about optimizing inference performance for transformers and a lot more. Before we do that, just a quick recap. A lot of the we are doing a lot more topics. This is an ongoing series. So if you head over to pytorch.org/events, you'll see all the upcoming talks. So you can go ahead and register. We'll be streaming on LinkedIn and YouTube. So there are other places to catch them as well. So before we dive deep in, let's do a quick round of introductions here. I'm Shashank. I'm a developer advocate here. And who wants to go next?
I can go next. So yeah, this is Hamid. I'm part of the applied AI team here. And mostly I have been working on model optimizations for inferences and distributed training. And with Mark, I'm one of the contributors to TorchServe as well. Yeah, pass it to Mark.
Thanks, Hamid. Hi, everyone. So I'm Mark. So like over the last year, I spent most of my time contributing to like open source ML ops tools in PyTorch. So I'm one of the main maintainers for TorchServe, but I've also contributed a bunch to Torch Data and TorchX. Recently, obviously, like now that we're all excited about performance, I feel like compilers are such a critical part. So I've been spending a lot more time on the 2.0 stack recently.
Awesome. Welcome. The 2.0 has been, as I mentioned, about performance, right? We've had a lot of talks recently about compiler, Torch Dynamo, Torch Inductor. We've had a lot of talks about performance, and a lot of it has been about training. And today we're going to talk about something slightly different. I heard a few things there. So there's transformers. Language models are all the hot thing right now. And I heard TorchServe too, which is the official serving framework for Python. So I know we're going to discuss both of them. So let's start by talking about language models and why it's important to speed them up. I know they're computationally intensive, and you want to reach sort of the right, I guess, target latency and throughput needs. So why is it important, and how do we go about speeding up language models?
Hey, Mark, do you want to take this one?
Sure, yeah. So I would say like at a high level, like there's sort of like an interesting like representational property in transformers where, it's like sort of tensor in, tensor out, and you can solve like a wide variety of problems. Like whether it's like text to text, whether it's like ChatGPT, whether it's things like text to image, like DALL-E. I think it sort of feels like a mainstream moment like for machine learning where like this is like stuff now you can talk about like with your grandparents and they can get excited about like what you're doing. And so but like the sort of like problem with these models is that like one they need to be really big to work really well, and the problem is if they're really big then they tend to be really slow, and if they're very slow they're not particularly useful, especially for inference, right? Like imagine if you wanted to do like autocorrect in Google and for like just autocomplete, and that took like 5 seconds, for example, per character. Like the product would be unusable. So at least like for us, like performance is like very much tied to like the usability of the tool. Like the faster you make it, the more places you can integrate it in. And I just think that's why it's like just so important to look at this problem. Unfortunately, it tends to be a very complex problem how to optimize them. But hopefully after this talk, like our goal is to make this problem somewhat clearer for everyone watching.
Yeah, that's a good point. Like user experience is so tied to the performance, right? I mean, accuracy of the model is one thing, but if it takes a few minutes to, I mean, we think of accessibility features, maybe text to speech or something like that, right? Or speech to text, and if it takes you, several seconds, even it has to be in milliseconds if you want a good experience. So yeah, that makes sense.
I would add that, think of it, if you want to serve these models in production for a long time, think what companies are doing. That's going to be super costly. So we need to cut the cost over there to help and democratize these technologies a bit more. And gives this opportunity to everyone to be able actually to afford and run these models in their production workflows. Yeah.
Yeah, we shouldn't forget cost, right? There's obviously user experience, but if it has to be under your target budget, right?
Yeah.
Then you want to have a balance. That makes sense. So, what are the, I guess, how have we been doing this? How have we been accelerating these on PyTorch today, and what are the things we're going to discuss moving
Mhm.
forward?
Yeah, maybe I can take this one. I can go and give a little bit of a background about what we have been doing so far, what is new in PyTorch that can help with that. Yeah, let me actually share my screen. Shashank, do you mind to
Yeah.
bring up my screen? Thank you. So I have a few slides here just to go. So originally, if you want to start from what is the problem here is that, as Mark mentions, these transformer language models, or generally transformer models, even if they are using for vision models, which are vision transformers mostly, they are very compute heavy and memory intensive. It means that basically we have a component of computation in these models that it can grow quadratically as your sequence length is growing. So if you are passing a bigger sequence length, you are gonna have a longer compute and more memory requirements as well. So this is challenging for both training and inference. So you are gonna run into this problem in both spaces. And the open source community and many of the hardware vendors, they come up with these like different solutions to make these transformer models more performant. But all of them are mostly on inference side. So think of like if you're familiar with NVIDIA faster transformer, Onyx runtime, TensorRT, projects like C-Translate, IPEX from Intel. So all of these projects help you to kind of optimize these transformer models and make them run faster for inference. Although if you have worked with them, you know that probably it's not super easy. It's not super fun. And usually to convert these models, that's a painful process. And so let's look at like what are they doing and why it's painful.
So
So
Hamid, I guess
yeah,
the trend I noticed in that is each of them are dedicated separate libraries for
right,
dedicated hardware, right?
hardware.
Some of them are NVIDIA specifics and some of them are like, so I guess a solution that lives in the framework level is more desirable from a user experience point of view versus something that's a little lower level that's on the
100%.
closer to the
Yeah.
hardware.
100% agree. Yeah, and that's our motivation actually here, that we want to cut that painful process somehow with an easier user experience. So all the libraries that we mentioned, you can see it on these slides on the right side, like from our own PyTorch TorchScript to Onyx runtime, TensorRT, all of them. The idea with them is that they want to capture a graph. So PyTorch has this dynamic graph that builds on the runtime. So we don't have ahead of time graph, computation graph there. So what they want to do, they want to capture this computation graph and optimize it through their compiler stack and do some of the normal things that compiler stack usually does, and remove the redundant ops, constant folding, and most importantly, like do kernel fusions and some memory planning. And some of them provides lower precisions as well, like int8, and even lower precisions these days. So this is what they usually do. But as Mark will talk about it later about graph capturing that we have and some of the problems and how PyTorch 2.0 is kind of solving that problem. So this is the general idea here. But as I mentioned, there is no unified solution first out there. So we have these tons of different libraries. They come with different sort of configurations that you know to know the best to make it work really. And at the same time, not easy to convert. So what we have in PyTorch, we thought that, as you mentioned, at the framework level, it would be great if we have like a fast optimized component. So now in PyTorch, we have this, yeah, So in PyTorch, we have these accelerated PyTorch transformers that provides you out-of-the-box performance. It works with eager mode, so you don't have to do anything, basically. You don't have to capture a graph. You don't have to go through the pain of converting your transformer model to different libraries and optimize it, maintain that code. So all that pain can go away. Although there might be some external, additional gains through some of those libraries, but overall, the main performance gain you can get it out of the box from PyTorch now. So this happens kind of
Hamid,
from
just to clarify for our viewers, right? This is the new thing, right? The accelerated P transformer is the new thing that gives you this out of box performance without having to go through all the compiler stuff that you showed, which could make any person's head dizzy if they're not a compiler expert. And I guess I know you'll address this, but the obvious question people will have is, how do I get like, is this there today? How do I get started? If you're going to answer them along the way, that's fine.
Yeah, sure. Yeah, I'm gonna get there very quickly. So yeah, basically, it has been out there. Part of it has been out there from 1.12. Which is for the encoder. So the encoder layer, the fast path for the encoder layer has been out from 1.12. We have done an integration with Hugging Face for that. I'll go through it. Then for the decoder, we have a new optimizations for the scale.products that it actually supports both inference and training. And if you look at here, basically, if you are using PyTorch from 1.12 onward, if you use these NN transformer encoder module, then you are in good hands, actually. So what you get is an optimized performance from this one. You don't have to do anything. And on the PyTorch nightlies right now, we have this optimized scale.product, which is living under NN multi-head attention here. So yeah, let's see what is better actually, and then why they are performing better and what we have done with them. So here for this transformer encoder layer, we made like a big code chunk written in C++ and CUDA. So, and we introduced two optimizations over there. One would be the padding, the smart padding, and the other one would be the fused kernels. So for a smart padding is what we do. We usually, when you want to do the inference, especially batch inference, you pad your sequences to be, the same length that you can pass it as a batch. This happens in training as well, but I would say that most of the issue could be like maybe on the inference side. And so what we do here, we do a smart padding. We remove the padded tokens that we don't need them for the actual computations. So, and only do the computations on the real tokens. On the and that actually can speed up a lot. Then the other thing we do, we fuse the kernel. We fuse a bunch of matmals and softmax over there and use, a better, we fused multiple kernels into one bigger kernel to kind of address the memory bound issue that we will go through it later on a little bit. And as I mentioned, we have this optimized scale.product. So anyone who look at this transformer block that you should be familiar, I guess, for everyone. We have these series of computation here, which is basically two matmals. You are doing matmal between your query key and your value at the end, and you run softmax on them. This is a chunk of the computation that we have in a transformer. This is expensive. And what we tried to do, we tried to optimize this using the new options that we have, the optimized kernels from flash attention and Xformer memory efficient kernels. So if you are using PyTorch nightlies, it's going to be released soon in PyTorch 2.0 that is going out in early March, I guess. You are going to get them over there, but for now, if you want to use them, you need to run on the nightlies. And under the hood, if you use, again, here, multi-head attention, you are going to get actually flash attention or Xformer memory efficient out of the box. So you don't have to do anything. you will get the performance over there, and it's transparent to user. And the good news is that it works out of the box with PyTorch 2.0 torch.compile as well. Yeah.
Okay, Hamid, just so I understand, just to make sure I understood correctly, I'm gonna say this again. Let me know if I understood correctly. So there are, when you said optimized kernels, so these are a fused kernels. So these are a bunch of ops that are fused, and they are written in a way that give better performance on the hardware than you would get by just using previously they would use different ops which were probably not optimized or not fused, right? So this is a
That's
faster.
right. Yeah. So
and
yeah,
is
basically like kernel fusions, what it does, it mostly say that you will have this memory bound issue to transfer your data from GPU global memory to the shared memory and do the computation. So if you each time transfer your data and just use and do a little bit of computation, you are spending most of your time transferring data between these two memories. So when you fuse the kernels, instead of running a very small portion of computation, you just string them together and make a bigger computation. So you transfer your data once and you do a big chunk of computation. And so you are saving this transfer time. And that's where you get the speed ups from these fused kernels.
Right. Okay.
So how about I show you an example? Because like I think this is really relevant. Just folks, like, because okay, like fusions are like in term when you think about like the compiler optimizations for ML. Oh, do you mind sharing my screen?
Yeah, sure.
Yeah. So let me just show you this. So this is the like documentation page for like, or like the marketing page from NVIDIA, like for their A100s. Okay, you look at this thing and it's like, let's say your TensorFlow 32 performance.
Could you zoom in a little bit if you don't mind?
Oh, of course, yeah.
Perfect, thanks.
So here, for example, you see like the FP64, or like, let's say the most impressive one will be the like the BF float and the FP16. Sorry, actually the INT8. And you're like seeing these like insane like numbers, like 600 like teraflops, right? Like or 300 plus teraflops.
And for those not familiar, this is tera floating point operations per second. So how many floating point operations it can do per second?
And so the metric of flops is like particularly relevant when it comes to like matrix multiplications. Like almost imagine it like a big O like notation if you've like done algorithms or something. But it's basically the number of floating point the number of floating points that you need to multiply by each other, individual elements, to be able to multiply like a matrix. Right. So this tells you that you can like multiply 300 teraflops of such of you would be if you had like a single matrix that had like 300 like tera elements, like I guess like that's yeah, so I guess like that would be like a thousand times 1,000. You'd be able to multiply those like in a single second. So you can just like think about it. You can multiply these like absolutely like insanely large matrices like in a single second.
Crazy fast, yeah.
But you look at this number, and you're like, huh, like what's going on here, right? Like you have like this number that's like close to like 1,000,000x larger than this one, and this is a problem. Like
memory bandwidth is how fast you can get.
Exactly. So it's like basically you can almost think of it like this. Like here, let me draw a quick picture. Like here,
I love
like so let's say this is like your GPU, right? And it's like, this is like, just speed, like sonic level speed. And then your memory bandwidth is basically here, like you doing like let's say torch dot tensor dot to device equals CUDA, right? So so this becomes the bottleneck, right? And not like torch dot matmul. Like let's say AB.
So this is the transfer, and that is the actual computation. So the bottleneck is in the memory transfer, not in the computation because GPUs are obviously very, very powerful throughput devices, but the bandwidth is what you highlighted is the bottleneck.
So and so let me show you an example of what people mean by like fusions in general. So let's say like I'm using Copilot here, so I'm cheating a bit. But let's say we had like we had like an N module like this, for example. And let's say basically I had like two operations that look like this. Let's say I had torch.cosine, torch.cosine, and then I had self.cosine2 equals torch. Actually, no, so it's going to be like this because we don't need to initialize these. Sorry. So let's say this was you had x equals torch dot cosine of x, and then you had x equals torch dot cosine of, let's say, sine of x. And then you want to return x.
Mm-hmm.
So let's say this is the problem you're trying to solve. And, obviously, like imagine, here, let me zoom in a bit more.
Perfect. Thank you.
Like basically, imagine that x is very, very big, right? So you're going to be transferring this to the GPU each time. And well, so let's look at this. Like, so let's say, okay, you're doing the torch.cosine. You have like one read from memory. You're reading the x, and then you need to write it back to the value of x, and then you have one write.
Mm-hmm.
And then, okay, you look at the sine, and it's like same thing. You have like one read, one write. So total in your program, you have 2 reads, 2 writes. Right? Whereas like when it comes to like a fused kernel, you can basically imagine if you had something that looked like this instead, where you said self of x. And this was like, let's say we created like a function, let's just call this like fused cosine sine. I'll explain how I'll explain how this works in a second, but let's say no, actually, yeah, it's a good guess, but not quite. So it's going to be like this. Let's say it's just cheating a bit, but I'll show you exactly how this is implemented in a second. And then I believe this is a sine. And so now, like what you would basically do is you're like when you're saying torch dot equals fused cosine sine of x, the 2 reads, the 2 reads and 2 writes become 1 read and 1 write.
Mm-hmm.
And both reads and writes like have a memory bandwidth implication, because when you're reading and writing, you need to send the data back over the GPU bus. So this is like, I think, the simplest example of like how to think about this. But let me just quickly show you now like how to think about this part, like how is this actually implemented. So let's take this example here. Here. So just to show you, for example, how this works in PyTorch 2, like we have a very similar example. So here it's 2 sines. What Torch compile does under the hood is it will generate a single kernel for this. And the kernel happens to be written in Python with a DSL called Triton, which was invented by a team at OpenAI. And you can basically here, you can imagine everything that shows up under a single kernel means it's fused. And so you see here the sine and the sine are fused. So great, like now we went from, so you can directly visualize what gets fused and what doesn't. So again, I don't want this to be like black magic. This is really like at a high level why this is important. And obviously, the bigger your operations are, the more complex they are, the more relevant this is. But this is sort of the simplest way to illustrate it. Here, I'll stop sharing the screen.
Yeah, the sure shot way to improve performance is to reduce the number of back and forths, right? Spend as much GPUs being that powerful. You showed the number of tops, float, how powerful they are at throughput, calculating these large, but you don't want to be going back and forth. Yeah, I've heard analogies about like school bus versus race cars. It's something like that, right? You can transport more people, whereas race cars you have to do many trips, right? Although race cars is faster, a school bus can take more people together at the same time. Yeah. All right, good, Hamid. That was a good, I guess, fundamental explainer in between.
Yeah. Great idea. Yeah. So yeah, can you actually pull up my screen?
Yeah. Go ahead.
Okay, so yeah, as Mark explained, so one of the main things that we did was this kernel fusion that can speed up a lot. And on top of that, we did that smart padding for removing the extra padded tokens as well. So we did. So as I mentioned, you don't have to do anything. Basically, this is available in PyTorch. You don't have to do any conversion or anything. But we did integrate it into Hugging Face. And the reason that we did need to do this integration is Hugging Face had its own implementation of attention layer. So we had to go do some mapping through the layers and ask actually Hugging Face models to call into NN modules, NN transformer encoder. And so details are available in this blog post here. And we have this collab notebook that I'm going to show you some of the speedups here, that how it looks in the code. So first of all, you need
if you don't mind, from a user point of view, let's say I'm a Hugging Face user. It's transparent, right? I mean, in the sense it's I don't need to worry about any changes from the user experience point of view.
That's what I want to show exactly. Okay. If you are a Hugging Face user, you need one-liner API to call, and that's about it. So if you are a Hugging Face user, you need to do that. But if your model have been written in a way that you are actually using NN transformer modules, you don't have to do it. You get the speedups. So if you are a Hugging Face user, so this is the collab that came with the blog post. You can go and try it for yourself. And this is specifically on the encoder side. So if using Hugging Face, you need to install the optimum library. And this is optimization library that Hugging Face offers. So you can install that one. And here is a list of the models that these transformer encoder layer, the FastPath, is supporting. So you can see that there is a mix from different modalities, from text to speech and even vision models. So what you want to do to really use that is you want to load your model. So you have a model name. If you are a Hugging Face user, you know how to use it. Then you can load it with pre-trained from, auto model from pre-trained, and you pass your, model name. So you load your model, normally what you do. And then to convert your model to a faster implementation, to a better we call it here better transformer, but actually it's accelerated PyTorch transformer. So you import better transformer from optimum library. And what you want to do, you just call better transformer that transform my model. And you want to keep the original model as well. And that's it. You got your new optimized models. So that's so simple for Hugging Face users. And what it does, if you look at these two prints that I'm not going to show you here, but it basically changes your layer names from original layers to converted layers. But let's look at some of the numbers maybe here, that what type of speedups we get. So we actually loaded a Roberta model, if I'm not mistaken, from the top. Yeah, we loaded a Roberta-based model from Hugging Face. And so to look at the speedups, we have a couple of helper functions here, like a benchmark or printing device. And let's see what we want to do here. So we are going to have batch size of 1 and sequence length of like 128. And yeah, that's about it. So we are going to test to see that how much a speed up we get this one. And this is a Google Colab, so it was running on a T4 card. So this is a T4 GPU. And if you see, if you run it, I have run it before, so just to save some amount of time here. So you can see that you get about 2.1x speed up using even for batch size 1. And batch size 1 is not exactly where you are using that smart padding or the sparsity that I mentioned before. So this is a good speed up for one line of change, right? And it's eager mode. There is no graph capture. It's not going to fail. So, and if you look at the same type of, workload on CPU, you'll again get some good speed ups. This is again batch size of 1 and sequence length of like 64. So it is not super huge too. And you get actually very small speed up here. And the reason is, you are basically doing a very small batch size and a very small sequence length here. So the main speedups from sparsity cannot be used. So to show you how you can use that actually, so if you just make a bigger batch for yourself, and then you pad it. So the way you pad it, it's gonna pad it to the longest sequence that it has in the batch. And then from here, if you run the benchmarks again, and this is still on CPU, if you run the benchmarks again, you will see that 2.1 x faster, even on the CPU for a larger batch size. And this is the batch size this is a batch that we have, and it has longer sequences for sure. So you can see that as much as, so let me actually show the similar numbers on GPU as well. So we are doing some random, input generations here, and we are doing different percentage of padding. So based on the sequence length, we do like 20%, 50%, or 75% of that sequence length as the padding. So we want to show the impact of padding and sparsity in these type of optimizations, how much you can gain and how much you can lose, in fact. So if you look at here, we just generate a bunch of different input sequences here with different padding length. And we run the benchmarks and we want to plot the results here. So what you see here is interesting. So as much as your padding percentage, it means that you have made longer sequences, but most of them are padding tokens. You can see that the speedups that you get is like up to 2.4x faster actually compared to your normal model. And this is similar with 8 and 16 16 sequence, 8 and 30 sequence length. And what you will see actually is that this is for a Roberta model. We have seen similar or even better speed ups if you go for like a Distilbert model. And here you can see that we got up to 4.x speed up. And again, that's a very cheap optimization. You don't have to honestly do anything. It's a one line of code, and that's what you get out of it. So it definitely worth of trying. And as I mentioned previously, it works for vision modes and audio modes as well. I'm not going to go through them, but similar speedups with different configs you can see on the blog post here too. But this is about the encoder layer. So whatever I talked about is about this transformer and an encoder. So Hugging Face models are just calling to this one. And what if you want to use these NN module, NN multi-head attention, which is using flash attention or basically Xformer memory efficient kernels? What if you want to use them? So basically what you need to do is that what they are doing again, they are optimizing the scaled up product. They are optimizing basically this computation here. What you want to do is, if you have a model that you are computing it yourself in your attention layer, just replace it with NN multi-head attention. That's all what you need to do. And you will get the speed ups. Okay. And if you are using this one already, you don't have to do anything. I'll show you this implementation here on a real code as well. So you can see here.
There's actually a couple of people asking where they can get access to the samples or notebooks. Is this example somewhere that people can go
this
read
one or the previous one?
I guess both. Whatever we're showing.
So yeah, the first one is definitely available here on this blog post. So there is a collab notebook here. This one. That if you basically go through it, you will get the same collab notebook. So that comes with the blog post.
Okay, I'll share that.
Yeah, and this one is actually from the new blog post that we just put out a few days ago. And this is how you want to accelerate stable diffusions with PyTorch 2.0 plus the acceleration for the transformers. These code snippets is mostly coming from there.
Awesome.
Uh,
I just shared both the links on the live stream. So thanks for your questions. And again, feel free to keep asking questions. This is really your show. We are here to share information, but it's better if we are focused on answering some of your questions about these new features. Go ahead, Hamid.
exactly. Yeah. So yeah, I just want to kind of show this one that, I mean, you see all the computations that we mentioned here as the scale.product. This is basically what you are saying here. You are basically doing a matmul between your query and key, and then you are basically adding the masks and do the softmax, and then finally you are actually computing. Do another matmul for the values. And if you can just avoid this by running even a scale.product attention, but this is not a pattern that we recommend, because you have to do these computations manually again. I mean, QB query values, but you don't have to do that really. Honestly, if you use just N and multi-head attention, that's the best pattern to use this new feature.
Yeah.
And
I guess the general recommendation is to, again, correct me if I'm wrong, like use the ones that are already available, because you and others have taken care to make sure that they are the most optimized versions, rather than trying to re-implement it yourself, right? The more you rely on these APIs that we already provide, the more higher chances that you're getting the best version of those functionality than having to implement yourself.
That's the exact intention behind like importing Flash attention and Xformer kernels into PyTorch core. We wanted to provide a unified, optimized way that everyone can use it. And we want to make sure that we maintain it. And if there are improvements coming up, like in next release, in future, we are going to add them into next releases as well. And yeah, definitely that's the idea here. And I want to stop here. I think I'll probably let Mark talk a little bit more about the other optimizations that we have in TorchServe, but quickly mention here that these are two PyTorch profiles from when we ran a larger.
Hamid, could you zoom in a bit? Like, I think it's like very, very small. Like.
Oh, oops. And if that helps, is it better?
A bit. It's still
and it's still small, I guess. Yeah. Okay. Let me see if I can go. Let me see if I increase the presentation mode.
It's good. No, it's readable.
It's fine.
Yeah.
Okay. Yeah. I mean, like I'll make the point, but so the idea here is that we saw that when we are passing basically larger workloads, like bigger batch sizes, longer sequences, we got better speedups with these transformer encoders. And I want to show you what is the reason actually. So here is a comparison between batch size 64 and sequence length of 256 versus batch size 1 and sequence length of 25, which is a very small workload. If you look at the profiles, you see that the first one, which is a bigger, which is a heavier workload, it is actually GPU bound. So the first one, these are the CUDA kernels on the top row that are launched from CPU. And these are the CUDA kernels, the actual CUDA kernels running on GPU. And you see that this line is pretty much occupied, and GPU is basically crunching the numbers here. Versus if you look at this one, there are these very tiny chunks of CUDA kernels running, and most of the time we are spending on CPU. And if you look at here, we have this very long CUDA device synchronized that basically CPU is waiting for CUDA to finish, for GPU to finish and get back to CPU. And this is the overhead issue that we have with Python, and this is the issue we mentioned. So this is a CPU bound issue. It takes time to transfer this data really to GPU. And the time that you spend on launching these kernels from CPU is much higher. And CUDA graph is something that could be super helpful here. And I guess that Mark is going to talk about it more, that how we are supporting in PyTorch 2.0 as well. Yeah, I'm going to stop here and let Mark actually continue. Yeah. So let me know if there are any questions.
Yeah, I love this graph. first view I was like, okay, this looks complicated, but now that you explained it, I love this graph because you're actually showing the two different paradigms, right? There's one
Yeah,
wherein the second one, which is like not just the data transfer, but launching a kernel takes time too, right? Every time you
exactly.
launch a kernel, which is a function that computes on the GPU, like it takes time each time you launch it, and that's true for any language when you launch a function. And you show how it's bound by the CPU, and in the first one, which I assume is the ideal state you want to be in, wherein you want the GPU
Exactly.
fully occupied doing its work, and the CPU is actually waiting for because in that case, you're fully utilizing the
Yeah.
GPU. I really like that.
Yeah, and that nested tensor, I mean, smart padding, that means a lot on a GPU bound work as well. Versus here, you don't get much use of it. So yeah.
Yeah. So they
So
have a question there.
Mhm.
I'll ask those, and then we could kind of continue our conversation. So there's a question which is about, we have a GPT dash J, um, 1/5 or 0.2 second inference time. I want to make it 0.2 seconds without beams decrease, and maximum 1 second for a batch of 50 users on Tesla T4 16 GB. How I so I'll take a stab at this,
uh,
and you're the experts, but it's really hard to make specific recommendations without knowing your specific workloads, right? At the same time, I guess question for Mark and Hamid: are there general recommendations you could provide to make sure that they stay within those bounds?
So
Um,
I can decompose this question a bit. So you're asking like you have a fixed model, right? And you want to make it faster. But you've already like hard coded a lot of parameters in this problem. Like for example, you're like, well, like can we do it on a T4? To which I would respond like, it's easier to upgrade your hardware. You're likely to get like much more significant speed up. So like
True.
maybe consider something like an 810G for the speed up. Uh, I think the other parameter is like, well, yes, like maybe the model could be smaller. Maybe you quantize it. Maybe you distill it. Maybe you pick a smaller model. Maybe you run it via like something like Torch compiler, use like multi-headed attention, even though I think the decoded support isn't there yet. Uh, but you can decrease like the batch size. So like I wouldn't fix too many aspects of your problem because like it comes at a cost, right? Like you have to either pay money to get better hardware, or you have to pay time if you're not willing to reduce any of your parameters. So it's more of like a pick your poison kind of situation.
I will add a little bit of color over there too. I think, as Mark mentioned, there are multiple variables here that is hard to chase without really knowing what is going on. So I have some general suggestions here that probably you can start with profiling your model. See, where is the bottleneck actually? Is it like a CPU bound issue? CUDA graph might be helpful.
Mm.
Is it like a GPU bound issue? Should you increase your batch size or whatever? There are different things. So I would say that start with some of the principles, basic principles. Look at the profiles, see what is going on. Second, I would say that if you are dealing with GPT style and generative style models, I think that KV cache is a thing that you need to consider. So the way that you want to cache previous tokens. So one of the issues with these other aggressive models is that you have to generate each token at a time. And for that one, you take all the past generated tokens and send it to the model for the next generation. This is actually the bottleneck there. And beam search on top of that. So these are all the factors that is contributing to this higher latency. I would say that if you can cache those previously generated tokens, look at the KV cache. I guess Hugging Face has an implementation of that, and there are a bunch of resources out there. So I think that would be something to look at that too. But again, without more specifics and looking into details, it is hard to make any concrete suggestion here.
Yeah. Thanks, Hamid. Thanks, Mark. I just a follow up from the same person who asked the question was, we use Hugging Face transformers for inference. We are looking to TorchServe. Is that a segue into some of the other topics we want to discuss today?
Sure. Yeah. Let me take a stab at this here. I'll share my screen. Here.
Actually, I think I jumped ahead. There was just one other question. If you want to take that and then transition, the other question was, does this logging also work with other GPUs such as Intel's XPU and IPEX?
Sorry,
Um,
you mentioned logging.
Yeah,
Yeah.
so I think they mean the PyTorch profiler in this case. I'm
Oh,
not sure, but I honestly doubt it. But like IPEX, sure, yes, and you could also just like use all of like Intel's like profiling tools, and we have a
Mm.
couple of case studies in TorchServe of people doing that. Yes, but just maybe like I think naturally like NVIDIA GPUs tend to get more attention than AMD's, than like everyone else is the profile. Other hardware vendors tend to come with their own profilers, I think, is traditionally what I've seen.
yeah.
Sounds good. Okay,
Um,
go
right.
ahead, Mark.
Let's switch to TorchServe then. Okay. So uh, here, could you mind? Yeah, just share my
Yeah.
screen. Yeah. So like as we mentioned at the beginning, like I'm one of the primary maintainers like for TorchServe, and the way you should think about TorchServe is it basically does all of the things that you need to do when you're running model.forward in inference, right? So this includes things like tracking like metrics, like logging, like auto scaling, and because like increasingly more, especially last year, the theme for us was performance. Uh, Users really were coming to us like for out of the box like suggestions for how to make like models run really really fast out of the box.
Mm.
So let me just show you this like quick picture here in our internals guide, and it helps because like this often answers questions about like, well, how's TorchServe different from Fast API, for example. Uh, is that like one, like you can basically have like a bunch of models that are deployed concurrently. A TorchServe instance will automatically swap in models in and out depending on like the scale. You also have like different RESTful APIs to manage models. So you can, for example, query the status, like unregister it, add more workers. You also have an inference API, so you can get like specific inferences from a model again. And this is like another one of those things, right? Like where like I said, like if people are asking me like, hey, like how do I make my TorchServe models faster? Well, like one thing, for example, is to like really carefully configure like the number of workers that you have. And so this is something we talk about like in our performance guide a bit more. But there's like a lot more that goes into this, right? Like basically, here, let me draw a quick picture. I sort of hinted at this when I was answering the question like regarding the GPTJ, but like when you think about like performance in general, there's like a sort of several series, several sets of optimizations to think about. Like one is like what I would call like your matmul optimizations, right? So this is like something like tile padding, flash attention, go into this bucket. Then you have what's like basically the model level optimization. So this is things like quantization, distillation, make a model smaller. So just you don't have to pick a huge model. Uh, Another one is like the framework level.
Mm.
So this is like in your inferencing framework. I mean stuff like configuring workers,
Mm.
your queue size, uh, like batch delay. So there's a couple of these configs, and then you have like basically what I would call like the hardware upgrades. And just to give you a TLDR on this, this really on AWS at least like refers to get a G5 instance for GPU or like an M6i for CPU. So these are like some really good like cost effective ones. And then we have like what I would call like the compiler level stuff. And this is like Torch Compile. This is Fusions and like memory planning and all this, right? So I know this is a lot of information, but the reason I want to show you this picture is that there's a lot of like knobs you can turn, and like without profiling, it's like really easy to just like optimize the wrong thing. However, like because in TorchServe, people come to us, they're like, hey, I want to make something fast. I don't want to have to go like read the theory of ML model performance. Like, could you help me out a bit? And I think that's like sort of what we targeted to make it a bit easier here. So I'm just gonna go like I'm just gonna quickly show you some like one really important file in TorchServe called the base handler.
But do you
So
mind to zoom in? Yeah.
oh yeah. All right. So I just want to show you like this really quickly. For example, like if you're using like I even say this like in the code itself, like get an A10G or an A100 if you're using Torch compile. Like this is how important this advice is, because for older GPUs, the memory bandwidth isn't as big of a bottleneck. And so you're less likely to see insane speedups from Fusion. So that's why often when people run things like like accelerated transformers or like Torch compile on older GPUs, and then they're like, hey, like why isn't all that much faster? Like, well, that's why, because you're sort of optimizing the wrong bottleneck, right? So specifically here, the way this works is like we sort of gate, we're like, look, is CUDA available? If so, is this an 810G or an A100? So this is like the architecture. And if so, this means this is shorthand for enable tensor cores. And so we saw from the NVIDIA docs that like the tensor core flops is like substantially higher than the FP64, which is often used for more scientific code, or FP32. And if you're not setting this, like you're gonna by default be using this, and so you're gonna be 10x reducing your peak perf. So these are like this is like a substantially important config variable, because it's just like one flag and you just get like 10x speedups. Going like a bit further here, a lot of like runtimes, like let's say for example TensorRT, for example, like they have this pattern where you have a model and you need to convert it. So for example, like let's say you torch script a model, and then you want to say like compile it with TensorRT. Here is an example input. So you have to be very precise about the specific like shape of your input data. And then you say like this is the D type, and then you say, for example, like run it with FP16. So for example, here like TensorRT mixes compiler level optimizations along with like numerical accuracy optimizations like quantization. But the tricky part about this is that they make you define what your input shapes are up front, which just like adds like a bit more hassle to it, right? Because whereas like with something like Torch compile, for example, you're not. You just pass in the model and you pass in a backend, which can also be TensorRT. So, but by default, it's inductor. And there's this important mode here called reduce overhead, which is absolutely critical for inference. And Hamid hinted at this earlier. So let me just show you quickly what this mode is. So if you go to the PyTorch repo, let's go here. So we're going to go to Torch, and then we're going to go to the init. So let's go to def compile. So this is actually the compile function. And you can see here it takes like a model. You can have like dynamic shapes, like different backends. And it has this parameter called the mode. And so you can notice here there's three modes. Like one mode is default. Another one is called reduce overhead. And another one is called max autotune. Max autotune really means find the right shape that your matrices should be in terms of padding them, or how the memory layout should be on GPU. So this is very slow to compile, but will be very fast once it's done. But the one we're paying attention to is this guy right here called reduce overhead. And reduce overhead within the context of Torch compile is equivalent to CUDA graphs. And what CUDA graphs do is, instead of like sending multiple small kernels to a GPU, so basically, again, memory bandwidth will be your bottleneck, you batch them all together and you send like one giant kernel. So it used to be the case that using CUDA graphs in PyTorch was somewhat complicated. Like you needed to muck around like with CUDA streams and do a whole bunch of stuff. And now it's like somewhat trivial. Like you just pass in this extra flag. And especially if you're running TorchServe with small batch sizes, this is just going to be absolutely critical. For larger batch sizes, it's not as big a deal, because you're going to be more compute bound as opposed to memory bandwidth bound, but the batch size obviously need to be pretty large. But again, this is like really like a really important flag, which is why like we sort of decided to just make it like a reasonable default. However, if you actually look at the release notes for Torch Compile within TorchServe, like we actually, for now at least, like discourage you from using it because like the inference performance isn't as competitive for GPUs as much as TensorRT or for CPU as much as IPEX. And so our general philosophy when it comes to like what is the right runtime, what are the right compiler tricks to use is like we don't know. You should just like benchmark and see, but we'll make it really easy for you to benchmark and see. So IPEX works the exact same way. It's just like a flag to optimize IPEX. There's also like Onyx support, so it like works like pretty much the same way. Here, where is it? Here. So where is it? Here. So in the case of Onyx, you need to set up like an ORT session. You need to allocate like your CPU, like the number of threads to be equal to like the number of logical cores on your CPU. And once you have an ORT inference session, you set up like a model. And so like also like this is like another important consideration. Like it's like I know the name Torch is in TorchServe, but TorchServe can like deploy like a TensorFlow model. It can deploy like an Onyx model, and we found that like it makes it really easy for people like wanting to migrate. And Onyx can very often be like the right framework to use if you want like good performance.
Mm-hmm.
Uh, TensorRT is easier because TensorRT like you just save it like it just looks like a regular TorchScript model. So because we support TorchScript models, we support TensorRT, and so most of the pain goes into preparing the model, which is basically the part that I showed earlier here. So this you wouldn't do within TorchServe, but you would do it right before going to TorchServe. So I'll stop here because I know this was a lot, but I just wanted you to be aware that there's like a lot of options, and what's right is very much like a benchmark and see kind of exercise.
Yeah, specifically, I think we were discussing this before the live stream to write inference. It's such a involved process. There are so many budgets. You have your latency budget, your throughput budget, and it's your different frameworks that you're working with and different optimization paths. I think ultimately, and different hardware choices that you can go through. Ultimately, you have to try out these options and see what works well for you. There's really hard to give a recommendation. I think like this is the best GPU and this is the best framework, right? You have to go through the whole process and see what works well for. I think that's been a recommendation I give always to. Thanks. There's a question here, which is with torch.compile, will there be dedicated lightweight inference engine that can be used standalone?
Yeah, so it's a great question. Yes, it already exists actually. It's torch.export. It's still like very much like I even like pre-beta feature, like expect BC breaking changes, accept bugs, accept like unparsable error messages. But if you're willing to go through the pain of it, like please like message us and we can like work with you on making it useful. But yes, I would say this is like a very like high priority ask. A lot of people have asked us for this, and it makes tons of sense. And I'm actually looking forward to integrating that in TorchServe myself. So I'm very much like also a customer here.
And to reiterate, I think we discussed this. A lot of what we discussed today is available in the nightlies, right? Not in the Torch 1.x. So it's in the nightly. So if you go get the pip install the nightly or go get the latest nightly Docker container, you could try out a lot of these capabilities. And if you have feedback, what is the best way to reach out? Mark and Hamid, is the Dev Discuss PyTorch forum, or is there a
GitHub repo issues, probably
GitHub
the
repos?
discussions. Yeah.
At us, yeah. Like, I mean, I
Okay,
like just
even better.
it's a yeah. Like either yell at us on Twitter, like add us on Twitter, add us on like GitHub. I think that's totally fine. Like, we both spend a significant chunk of our day on both of those social platforms. So,
That's,
whatever works for you.
yeah, that's nice that you're being so approachable because, yeah, I guess we want to reduce the barrier to providing feedback. If you put
Mm.
so many layers between the user and the person taking the feedback, it makes it so that's good. But yeah, as I mentioned, there are a few different forums, right? DevDeskus is pretty active. There are a lot of maintainers and contributors who spend time there, and you could obviously reach out directly to Mark and Hamid too via these channels. As we have, I guess, a minute left of the live stream, but are there any last things? There are no questions, so last things to reiterate before we close. Mark and Hamid, closing words, if you will.
Sure, yeah, I have a quick one. So I don't know if you all like know the sort of the expanding brain meme, but I sort of want to like translate that to performance, right? So I think like the very like I would say like when you're thinking about performance, sort of like the level one is you like hear some advice about how to make models faster, and then you leverage it, right? Level two is you yourself figure that out and you write a really good blog about it, and people go figure it out. Level three is you sort of make these things more like out of the box, like supported in your code with like various config flags or warnings or errors. And level four, which is why I'm personally so excited about Torch Compile, is you just make a compile like think about all of this for you. Like the parameter space is too big. Humans aren't meant to deal with this kind of complexity. So I'm very excited about compilers for the potential of automating like model perf improvements.
Yeah, that's where technology is heading, right? The early technologies are always a lot of DIY, get your hands dirty, but once it matures, it's a lot more straightforward, and hopefully you'll get out of the box performance without having to do anything. All right, folks. So we're coming to the end of the live stream today. I just want to reiterate that this is an ongoing series. We've had several of these. You can find a list of links in the pytorch.org/events. All the previous live stream, including this one, will be available on the YouTube channel. If you're watching this on YouTube, you know where to find it. And be sure to come back and register for the upcoming live streams. And if you're on YouTube, you can also like, subscribe, get notifications directly there. Or if you want a calendar invite, go to the PyTorch website and click register. So we'll close here. Thanks again for spending your time with us, and hopefully we were able to answer some of your questions and share some knowledge that you previously didn't have. With that, we'll close here. So that's bye from me, Shashank, and
Thanks, everyone.
bye
Thanks
from
for
me.
listening, everyone. Thanks,
Thanks.
Shashank. Thanks, Hamid.
See you in the next one. Bye.
See you guys.